Greetings and welcome to Distillate. In today's lecture, we are going to talk about ordinary differential equations. So, ordinary differential equations are some things that you'll very often come across in many branches of engineering, including chemistry. So, we'll talk about ordinary differential equations and learn how to solve them numerically using Python, right? So, uh, any ordinary differential equation can be written in this form. Say an dny by dxn plus an minus 1 dn minus 1 by dxn minus 1 and so on till a1 dy by dx plus a naught y is equal to some function of x and y. Right. And by the way, the ANs, the AN minus 1 and so on, all of these coefficients as well can be functions of x and y, right? And this is the nth derivative, this is the n minus 1th derivative, and so on, right? The order of this differential equation over here is n, because the highest derivative over here is the nth derivative. So it's an nth order derivative. And yeah, so that's the differential equation, right? Uh, so let's start with simple differential equations. So let's start with the first order differential equation. So the first order ordinary differential equation is of the form, say, dy by dx plus some function of x comma y times y equals to some other function which is qx comma y, and we can take this thing on the right hand side and we can finally write this entire thing in this form, right? So any first order ODE can actually be written in this form, right? So now this becomes a first order ordinary differential equation, and since it has one derivative in it, so therefore we'll need one condition to solve this problem, right? Now this one condition could be a boundary condition, or since we are dealing with just one condition, so rather than calling it as a boundary condition, we'll call it an initial condition. So we'll need, let's say, the value of y at some initial point, say x naught, and using that initial value, we are going to move ahead in x, right? A more common example of this is an ordinary differential equation in time. This is something people relate with more often. So this is a very literal initial value problem where you need an initial condition. So the initial condition means you need y at time t equals to 0. And using this y, you eventually end up solving for various values of I at different times, right? So this is a more general case of that, right? And since you need an initial condition in this case, these kind of differential equations give rise to what are known as initial value problems. So initial value problems require you to specify an initial condition along with the differential equation, right? And you can use the two to solve the problem. So for example, if you have, say, a problem of this kind, minus dca by dt, we just solved this in the previous few lectures, equals to k ca to the power n, right? We also had a more complex problem. We had cb to the power m, but let's just try to ignore this for now, right? So this kind of a problem becomes an initial value problem, where the initial value is this, right? This is the initial value. So now you have to solve this problem, right? Now, this can definitely be solved analytically, but as the problems become more and more complex, you look forward to solve these problems numerically because solving them analytically becomes very challenging, right? So we'll try to learn how to solve this problem analytically, yeah, numerically, right? So numerical solutions of ODEs. In today's lecture, we'll talk about only one method, which is something that I very often use. So it's a very nice method, very useful and a very convenient method. But over time, we'll learn about more such methods. But in today's video, we'll talk about just one method, right? But in general, the numerical solutions of ODEs could be explicit in nature or implicit in nature. So let's try to understand what do we mean by explicit solutions and implicit solutions. So um, in the case of initial value problem, let's try to explain it from the initial value problem perspective. So in the case of initial value problem, you have, let's say we are trying to solve dy by dx equals to f of x comma y with the given initial value that at x equals to x naught, at x equals to x naught, y is equal to y naught. So this is the initial value that is known to us, right? So in order to solve this, we'll have to march forward in x, right? So we'll have to march forward in x. So basically, what I mean to say by that is that let's say we have y versus x. This is my x naught. Corresponding to this is my y naught. So this is the point that we are starting from. And then we are going to march ahead in x. So let's say this is at x1, this is at x2, this is at x3, and so on, right? So we are going to march ahead, right? So if we use an explicit method, right? So an explicit method, in order to evaluate y1, right? In order to evaluate y1, an explicit method would only use the information at y naught, right? X naught and y naught, right? So whenever you have to evaluate y1, okay, I'll write down over here. So if using explicit method, in order to evaluate the information at y1, we'll always use all the information that is available at the previous points, right? So x naught comma y naught. But if we use an implicit method, so an implicit method would involve, so in order to use an information at in order to evaluate the information at 1, the first point y1, we are going to use information at both the previous point as well as the given point. So we'll do both of them. And this makes this kind of a solution non-linear in nature, right? This becomes non-linear, and therefore when you solve the non-linear equation, you end up getting y1, right? So for example, let's say you might get y1 equals to y naught plus, say, a x1 squared plus by1 cubed, something of this kind. So now y naught is known to you, x1 is also known to you because that's the next step in x, so that is known to you, right? But y1 is an unknown. So this is a non-linear algebraic equation that when you solve, you will get a solution for y1, right? And that's the point that you're going to choose to assign to y1, right? So these are the two types of solutions. Both of them are useful. Explicit methods are mostly useful because they are simple, they're simple to code, they take lesser time to solve, to compute. Implicit methods are useful because they are more accurate, they are more stable. So when I say more stable, that means that if I change, let's say, the step of x, let's say, if I say that x1 minus x naught is delta x, so that's the step of x. So if I increase the step of x, if I increase delta x, it's possible that the solution might become oscillatory in nature, which is not true for the actual solution. So let's say the actual solution might look like this, but if I increase the step size too much, the numerical solution might start looking something like this, which is an unstable solution, right? So the range of delta x is more for an implicit solution, for an implicit method compared to an explicit method. So in an implicit method, you could span a greater range of delta x without the solution being unstable. While in explicit method, there's a limited range of delta x. So that's not something that we are going to worry about right now, because we are going to deal with simpler problems. But as you go into more complex problems, stability analysis becomes an issue. So yeah, I learned about this during my grad school, but yeah, maybe over time we could learn about this in the videos that I have. But anyway, so we are going to talk about explicit methods for now. So explicit methods are where, in order to evaluate the information at the point y1, we are going to use the previous point, which is y0, right? Similarly, in general, for explicit methods, we are going to use information to evaluate the information at the point I plus 1. We are going to use all the information at the previous point. So some something of this kind, right? And since this is completely known to us, this entire RHS would always be completely known to us. So you directly get yi plus 1, right? So one of the explicit methods, one of the simplest explicit methods, is the Euler's explicit method. So Euler's explicit method involves using some, okay, this is not a good pen. Okay, that's the marker. Okay, so the Euler's explicit method involves using yi plus 1 is equal to yi plus delta x times fxi comma yi, where fxi comma yi is just whatever was in the RHS of the solution, of the differential equation, right? So if you write a differential equation in this form, this is what fx comma y is, the RHS, right? So once again, you see, at in the RHS of this solution, we see only yi, right? So we have yi, we have xi yi over here, and because of that, this can also be computed very easily. So we don't really need to solve any non-linear equations in order to evaluate yi plus 1. That's why it's an explicit method, right? This is the Euler's explicit method, and this is something that I very often use, right? Now, one way to code for this particular method is to define arrays. So we start with arrays for, say, x, right? So for Euler's explicit, so for this ordinary differential equation, we'll obviously have some a given initial condition. So let's say this is the initial condition that we are starting with, right? So we'll start with an initial array, which is this and this, right? And over time, as we move forward in X, we are going to append new values to this array, right? So that is what we are going to do. We'll also define the step delta X, which could be anything, right? And once that is done, we could, so with the Euler's explicit method, or in general with ODE solving, I generally use the while loop because I like to specify the final point till which we need the solution. So let's say I am specifying that XF is the final, the last point at which I need the solution, right? So I like to specify that. And based on that, I say that while this, whatever is the last element in my X array, while it has not reached XF, we can go on. And as soon as it reaches XF, we have to stop, right? So this is what I generally write as a condition, right? And once that is done, after that, we start uh, appending new values. So uh, So in general, you'll always write xi plus 1 is xi plus delta x. So xi is the last value in the array. So that's x minus 1, right? So x dot append xi, sorry, x minus 1 plus delta x, right? So this is what we append to the x array, and to the y array, we append this thing. So this over here is the last value of the y array. So y minus 1. And this over here is once again the function evaluated at the last value of the x array and the last value of the y array, right? So that's why, since the last value over here has changed, that's why I like to perform this step once I've already appended the y array. So this is the next step, because in this case, the last value would change. If you are doing this first, then we are talking about the second last value here. So this becomes x minus 2, right? But to avoid any confusion, I would perform this operation at the last, right? And finally, over here, I'll say y dot append the last value of the y array plus delta x times the whatever the function is. So I'll evaluate the function over here at x minus 1 and y minus 1, right? So that is what we are going to do, right? So for example, in case of this thing, minus dca by dt equals to kca to the power n, this is going to be actually minus kca to the power n is going to be the function, right? So we'll just write over here as minus k times ca. In this case, ca is y. So y minus 1 to the power n, right? That is what we are going to write for this equation, right? So that's how you code it out, and it's a very simple code. So we could try this out later on. But before I move ahead, I also want to talk about what are known as coupled ordinary differential equations. So coupled ODEs, and this is something that we'll very often use. So I'll talk about these. So coupled ODEs involve more than two variables. So for example, if you have an ODE of this kind, dy by dx is equal to some function of x comma y, right? You could have another variable, say dz over dx, which is some other function of x, y, and z. So both of these could be functions of x, y, and z. And that makes these two ordinary differential equations coupled, right? Now, if you use implicit methods here, it becomes even more challenging because now instead of solving a single nonlinear equation, you have to solve a system of nonlinear equations, right? But since we are dealing with explicit methods right now, more importantly, we are dealing with Euler's explicit method right now. So this actually becomes very simple. So all you have to do over here is that you have to use this equation to evaluate yi plus 1, and you have to use this equation to evaluate zi plus 1. So you can write yi plus 1 is equal to yi plus delta x times fxi yi zi, and similarly zi plus 1 can be written as zi plus delta x times g xi yi zi, right? And yeah, that becomes a very simple way to solve this problem, right? In general, if you consider this entire thing to be, let's say, a vector capital Y I plus 1, and this thing as another vector capital yi, and these two as another vector some f at evaluated at uh, um, yi comma xi, right? So in that case, this system of ODEs, the solution to the system of ODEs can be simply written as this times f yi comma xi, right? That's the Euler's explicit method. And now this would be applicable for any number of ordinary differential equations, coupled ordinary differential equations that you can write in this form, right? So all you have to do is you have to write a vector of all the y's. You have to write a vector of all the functions, right? So the first line would have the function associated with the first ODE. The second line would have the function associated with the second ODE, and so on. And that's it. You're done with that. So that's actually a simple way of solving this system of ordinary differential equations. So one thing that I often like to do of when I have to deal with coupled ODE is deal with a very simple example, the one that we discussed in the previous lectures. So we are going to solve, let's say, an ODE of this type, KCA to the power n, CB to the power m. Now over here, you see there is another variable CB, right? So technically, you could use stoichiometry to solve for CB, but let's say we don't use that, and let's say we try to use the rate expression for CB as well. So we'll say minus dCB by dt is also equal to kCA to the power n CB to the power m, right? Although the easier method would be to say CB equals to CB naught minus CA naught minus CA. But let's not do that. So this is the way you would do it. But let's say it's a different thing. It's a magic sort of a thing, right? So let's say we are trying to solve this. So once again, we'll make uh, the C, let's call it, once again, let's call it yi. And in this case, we'll start with the initial condition. So let's call it y naught. So y naught, which is going to be initial CA naught, CB naught. And the function vector is also going to be a very simple one because both of them are the same. So we'll just say k CA naught to the power n, CB naught to the power m. And this is going to be k CA naught to the power n, CB naught to the power m with a minus sign, right? And just y1 equals to y naught plus delta t times f, right? And this has been evaluated at y naught, right? That's it. That's the solution of this ordinary differential equation, right? This coupled set of ordinary differential equations, right? So I would highly recommend for you people to try writing the program for this particular type of equations in Python. And I'm very sure that you can do it. We've already seen how easy it is to write a program in for a single ODE, and you can simply write the program for coupled ODEs as well, right? I'll leave it as an exercise for this lecture, and we'll discuss about this kind of a program in the next lecture. But I would highly recommend that you try to write this program yourself, right? There's one last thing that I would like to discuss, and that is higher order ordinary differential equations. So now, since we have learned how to solve coupled ODEs, we could go ahead and try to solve higher order ordinary differential equations. So let's say we are trying to solve an equation of this kind: at squared y by dx squared plus b dy by dx plus cy equals to some function of x comma y, right? Something of this kind is what we are trying to solve. Okay. Now, since we are dealing with initial value problems, so in initial value problems, we'll only provide the the values at the initial point. So all we are going to provide is the value of y at the initial point. And since this is a second order ODE, we need two conditions. So since it's an initial value problem, we have to provide the other condition as well at x equal to x naught. And we are going to provide the derivative at x equal to x naught. So that is how you define a higher order initial value problem. So let's call it, excuse me, let's call it z naught, right? So this becomes a properly specified initial value problem, right? And now let's try to solve this problem, right? So a very simple way of solving initial value problems for higher order ordinary differential equations is by doing this very simple substitutions. So you substitute dy by dx as some z, right? And therefore, the second y over dx second becomes dz over dx, right? So you are able to write this first equation over here as a dz over dx plus b z in place of dy by dx plus cy is some function of x comma y, right? And then what you can do is you can take all of this towards the RHS, you can divide it by a, and you finally get the equation in the form of some function of x, y, and z, right? That's how you write dz over dx. But remember, this is just one equation. You need two equations, right? So the second equation, because there are two variables, two dependent variables, y and z. And the second equation comes from here. This is the second equation. So the second equation becomes dy by dx is equal to z, right? Which is technically a function of x, y, and z, right? So this is the second equation, right? Now let's specify, this becomes a first order ordinary differential equation. This becomes a first order ordinary differential equation. So we need one initial value to specify this problem completely. So since we know that at x equal to x naught, we know z, right, which is dy by dx. So we know z at x equal to x naught. So that has been specified over here, right? And the second condition is, of course, at x equals to x naught, we know y is equal to y naught. So this is a very nicely specified system, and therefore you can eventually end up solving this problem very easily, right? So all you have to, this is again a coupled ordinary differential equation. So all you have to do now is yi plus 1 is equal to yi plus delta x times f of yi comma xi, and the f vector over here is nothing but g xi comma yi comma zi and zi. That's it. That's the f vector, right? So that's how you solve a second order ordinary differential equation. Even if you go to a third order ordinary differential equation and you add another term, say d third y by dx cubed. So in that case, since this is a third order ODE, you'll have to specify 3 points at three values at x equal to x naught. So we could specify y equals to y naught, dy by dx equals to some z naught, and d second y by dx squared equals to some u naught, right? And then that again becomes a simple system of 3 ODEs, right? 3 first order ODEs, and that once again can be solved. So any higher order ODE can be solved using this simple substitution over here, right? So that actually makes it very, very easy, right? One thing that I would recommend trying to solve is trying. So this is just an application of this kind of a problem. So it's an equation of this kind. Or let's not go to that. Let's do a chemical engineering problem. So we have all come across the diffusion convection equation. So d second c by dx squared minus v dc over dx plus some rate term. So let's just call it k c to the power n equals to 0, right? This is a diffusion convection equation, right? So once again, this is a second order ODE. And let's say if we specify the concentration at x equal to x naught and the flux at x equal to x naught. Let's say we have, okay, let's just specify the flux. So dc over dx equals to some given flux n1 at x equal to x naught, right? So now this becomes an initial value problem. This entire thing becomes an initial value problem. And now we can solve this problem using the method that we just learned, right? So I would recommend you all to try to at least set up this problem the way we've done in this section over here. And then we would try to solve many such problems using Python. So that would be all for today. Thank you.